This is exactly how Find Contours edits the image. It does some sort of overlay with the contours, so this is why it looks like this. You probably won't ever need to use this image, so but keep that in mind if you're ever playing with your Find Contours function. Alright, so let's actually see the contours now. So this is perfectly done. These are 3 contours that have properly segmented our black squares here. So you've just ran your first contour extraction code. And as you can see here, it actually outputted that we've created or found 3 contours, which is exactly as we saw. So now let's do some other interesting things with contours. Let's take a look at the actual contour file. So let's actually print the contour file here that we extract. So let's do print contours. Let's run our code. There we go. So here we have a matrix, or it looks like coordinate points, XY points of contours. So what exactly are we doing here? So OpenCV stores contours as a list of lists. And what a list of lists is that, remember when we ran the length function on our contour file, we saw length being 3. That means there are 3 lists of lists in that file. So imagine contour 1 being the first element in that array, and that element contains a list of all the coordinates, and these coordinates here are the points along the contour. Now there are different ways we can store these points, and that's called the approximation methods, which we'll come to shortly. Okay, so let's head back to our code and I'll teach you a bit about approximation types. So as you saw here, when we printed our contour file, we saw a bunch of points here. So these points are actually the points that lie around the contours that we just saw, those green squares or rectangles around our blocks. So let's look at the notes here on approximation methods. Now there are 2 approximation methods here. There's chain approx none and chain approx simple. Now difference between these two is that chain approx none actually stores or gives you back all the points along those green lines there. So it's going to be a ton, or an exorbitant number of points. However, chain approx simple actually gives you the bounding or the endpoints. So it gives you basically like a polygon. So if it's a square, it's actually just going to give you 4 points. If it's a triangle, 3 points. So this is a much more efficient way of storing contour points. So just keep that in mind if you're finding contours in large images or large sets of images. So we're going to talk about retrieval mode. Okay, so let's actually take a look at retrieval modes now. And retrieval modes are sometimes a bit confusing. Actually, to me, I found it a bit confusing the first time I looked at it. However, they're actually not that confusing, and they're basically just 2 main types that you'll be using in most cases. So let's take a look at the types here in our PowerPoint slide. So retrieval mode essentially defines the hierarchy of the contours. So hierarchy being like, do you want sub-contours, or do you want external contours, or do you want all contours? So let's look at the 4 types of retrieval modes here. There's retrieve mode list, which returns all contours, which is good if you just want everything. There's the retrieve external, which gives us only the external contours, and I actually find this to be probably the most useful one in most cases. However, there will be times you'd want a contour that's within a contour. Imagine like a donut shape, perhaps. There's retrieve comp and retrieve tree. Retrieve tree is actually also very useful as well. I said the first 2 are the most useful, however, tree is actually very useful. Tree returns, I'll tell you why. Tree returns the full hierarchy information of that. Now, hierarchy information is a bit confusing, and I'm not going to discuss it in length here unless you guys wish for me to do it. I think in most cases you don't necessarily need to understand them too much, but if you want, you can click this link here and actually get a very detailed tutorial on hierarchy modes here. So just to simply illustrate something here, by setting the different retrieval modes, our hierarchy file, because if you remember correctly, let's look at the code again, define contours function returns contours and hierarchy. And if you were to look at hierarchy, hierarchy would actually give you this contour, the present layer, I guess you can consider it like a layer, the next layer, and the first child and the parent. So these are a bit confusing, so I suggest you read this just to get some more information here. Okay, so let's go back to our code and illustrate the difference between the first 2 contour types. Retrieve list, which retrieves all, and retrieve external, which retrieves the outer contours only. Okay, so let's take a recap at what this did here. So we see we've got the contours there. So let's change our file now to another file here in our directory called donut. It's a square donut because it's a donut shaped square. Sorry for the bad terminology. So that's our donut shaped square on the left. As we can see, we've got the 3 external contours, but the contour inside has been totally ignored. So now let's change this now to list. Sorry. Let's run this code again. And there we go. So we see now list retrieves all contours, including the inner contour in this square. So that's a good example of how their different retrieve modes work. So when you're implementing some projects later on, please always consider whether you need to get external contours only or whether you need to get all contours. And in future, if you do want to extract inner or outer contours only, you can use functions like retrieve all or retrieve list, and actually use hierarchy to actually identify different layers or levels of contours, which is quite cool. So that concludes our gentle introduction to contours here. Let's now look at sorting contours. We can sort from left to right, or we can sort by size. So that's pretty cool. So let's take a look at that. So let's talk a bit about sorting contours. This is a surprisingly useful technique when applying object recognition algorithms or machine learning classification algorithms. Sorting contours by area, which is the first technique we discuss, helps us eliminate small contours which may be picked up as noise, or extract the largest contours, which may be the most important parts of the image we wish to analyze. Furthermore, sorting by spatial position allows us to sort characters. Suppose you're looking at handwritten text. It allows us to sort characters left to right, which is exactly how our brain processes it. So now let's take a look at these sorting algorithms I've developed in the code. Okay, so let's open lecture 4.2, sorting contours, in our IPython notebook. Okay, so we see some code here. So before we actually begin explaining this code, I invite you to run this code. So let's run it together. So these are our 4 shapes here: square, triangle, smaller square, and circle. These are the canny edges that we extract from that original image. These are the contours, and this is something new I wanted to show you guys. What I've done here, I've taken the contours from the original image and drawn them over a black background. This way we can actually, this is a good technique in actually looking at contours separately from the original image. And these are the contours overlaid on the original image. This would be helpful in case, like, imagine we had a green image here and you didn't know if the contours were drawn correctly. That's why we do this. At least that's why I do this occasionally, so I can see the visibility of my contours quite clearly. Okay, so let's close this and then we'll begin sorting. So if you're curious as to how I created a blank or black background image, I simply use numpy zeros function here and use the same dimensions from our original shape, and then put 3 layers for the RGB colors here and call this black image. And then we draw this over here, draw contours over our blank image. So this is the contours file that we extracted previously, and that's simply it there. Okay, so let's scroll down now to see how we actually sort by contour area size. Okay, so before we begin going through this code, let's just run this code and see what happens. So this is the largest contour here, square, and it's highlighted first, then the circle, then the triangle, then the square, the smaller square. So we can clearly see we're sorting by size here. So let's see how we do this now. So firstly, one thing you should note in IPython notebooks is that we actually defined or found our contours here in this previous cell. However, we can reuse that contour file here. We don't need to actually run that line again using IPython notebooks. All the variables that exist here are also available to use here. So that's something you should keep in mind. So let's actually see how we sorted by contour size. So you can see we printed here the sizes of the contours here. This is the unsorted size, and this is after sorting, and you can see it's in largest to smallest here. So how did we do that? That's done by this line here. This is sorted as an OpenCV, it's a Python function that takes into consideration, this is the contours that we're sorting. This is the function that we're passing the contours to. So we're passing every element in the cell to this function here. And this is the order. Reverse equal true means we're sorting from large to small. False means we're going from small to large. So contour area is an actual OpenCV function, and we use it here. In this function I define up here. This function simply takes the contours that we created up here And what it does, it loops through each contour in that contour file, and it calculates the area of that contour. That's what cv2.contour area does. It calculates the pixel areas, the area of the contours in pixels for each contour. And then we return this array here, this array called all areas here, and that's what we print here. So we printed it before and after sorting. And then, as you can see, we step through or loop through each contour by size. That's done in this 4 lines right here. So we've saved our sorted contours as sorted contours, quite nicely named. And for each contour in the sorted contours, we're drawing the contour over our original image. This is the contour we're accessing here. -1 again, saying that we're drawing all contours, even though in each case it's one contour we're looping through here at a time. The weight key allows us to step through key by key so we can see the contours by area, and then we're showing it here. So that's basically how we sort by area. We're now going to move on to how we sort contours by left to right, which is a bit more involved. However, it's quite simple as well. Okay, so let's move on to sorting contours from left to right. Now this code is a bit more involved. However, it's actually not too difficult to understand as well. So these are some functions I define here. We'll get into that shortly. So we load our image and make a copy of our image here, and then we use this here to run basically a labeling function on our contours. Again, I'll get into that shortly. And basically this is, again, we sorted here by our own function. Remember previously we sorted by using OpenCV's contour area. We've now defined a function called x coordinate contour. As you can imagine, this sorts by the order of the x coordinates. Hopefully that was self-explanatory to you. And then we run a loop here. This is a loop where we actually label our contours left to right. And in case you're wondering what enumerate means, enumerate basically allows you to count this variable here, I. So every time the loop runs, so every time it's going through 4C in contours itself here, it's incrementing I. And we use that to actually plot or actually count or label the order of the images here. And there's something else going on here which I'll describe shortly. It's about cropping contours. So there's a lot going on in this code. So let's quickly run it and maybe you'll get a better idea of what's happening here. Okay, so let's quickly discuss our first key function here, and that's the x coordinate or x coord contour. What this function does, it returns the x coordinate of our contour centroid. Now centroids, we haven't actually dealt with that yet, but what centroids are, basically we use this OpenCV function called cv2.moments, and what it does, is that it takes the contour in question here and it actually returns the center point of it. So later on here in this other function here, you can see we have moments c, which is our contour in question for this function here, and cx and cy based on the moments here that we calculate here. This is roughly the center point or center of mass. You may have heard that term in physics before. So this is the center of mass of the contour, the x position and the y position here. So once we extract the x position here, that's what this line is here. As you can see, it's the same code as this line here. That gives us the x position. So that's how we can actually sort using the sorted function here in Python. So what this does here is that this returns the x position for each contour that's been inputted here. And we sort from smallest to largest here, mainly because we're going left to right. As you remember, OpenCV has a top left corner from 0 position. So going from left to right is basically small to large. Okay, so the other parts of the code that may be interesting is, firstly, let's see how we labeled the center of masses or on the contours itself. So what we do here, this function I created here, takes the image, takes a contour. Actually, we don't use I anymore, so you can actually delete I. It doesn't actually do anything. And you can delete it here as well. So it's a redundant thing. Maybe I was editing the code previously. So anyway, what this does, it takes the image and the contours, and it actually draws a circle at the center of mass for each shape here. Then it returns the image back to it right here. So that's what this does here, and it edits the original image here, and we have the centers highlighted in each of the image. So let's take a look at that again. There we go. And then we label it left to right, right here. Okay, so now let's look at the third key important part of the code here. which we've done the labeling and stepping through before previously, so you should have a faint idea of at least what's going on here. If you don't, I can quickly go through. What's happening here is that we're plotting the label according to the order here. Label being I. What we're doing here is actually looping through the contours here, and again we're doing this enumerate type loop, which we've seen. Actually, we haven't seen it before, so this is the first time we're actually seeing it here. So what enumerate does, it enumerates, it goes through, it loops through this contour file here, and what it does though, it actually iterates I each time it actually loops. So we're using I to be basically the order. So I plus 1, because I starts at 0 unfortunately. So we add 1 here. So using the put text function here, we're putting text here at the center point of the image here. So let's take a look at that again. So we see the center points previously drawn here. That's what we highlighted before. And now instead we're actually putting digits using put text at the center of each contour. Now you can see it's not directly, the labels don't always come up in the direct center. That's because the point is here, but put text generates the image. Basically, I think it's at the top right of that point. So that's what's going on here. The second part of this code here, this loop I should say, that's interesting, is that we're now cropping our contours. Cropping our contours is something we didn't discuss before, but it's actually very useful, especially when you're feeding it to a classifier. So how we're doing that is that we're actually using this OpenCV function here called bounding rectangle. And what that does, it actually gives you the rectangular overlay of a contour. So in a square and rectangle, it's the contour itself. However, in a triangle, it actually is the square block at the extreme points of the rectangle. So by using bounding rectangle, we extract the four extreme points, x, y, w, h, and I'll discuss a bit what that means secondly. Actually, I'll do it right now, so you get an idea of what's going on. X and Y are basically the starting points of the first contour. So imagine you have a square and you have a top left starting point here where this mouse cursor is. Hopefully you can see it. And width and height are basically the width here that extends this way and the height that extends down over here. So that's actually how we get the bounding rectangle here generated. And using NumPy, which we previously saw, we can actually crop images here. So we're going from Y to Y plus H. And the reason it's plus H for is because I said it gives you the height and the width of the image here. It doesn't actually give you the endpoint, the actual coordinates. It gives you the length of pixels. It goes in that direction. So it has to be Y plus H and X has to be X plus W. And what happens here is that we're actually cropping the image here. And we're creating a file name here called image name. So we're concatenating some data here to be a string. So it's output shape underscore the string name, well, the string number converted to a string, I should say, and the file end type here. And we're just printing it every time it goes here, so we know we stored 4 images here in that file. And I'll actually open those files for you shortly, because what we're doing next is actually writing those files to our hard drive. The reason I have this here for is actually this is extracted from another project where I was writing files to the hard drive and then using those files to input into a classifier for object detection. So we can just quickly look at those files now. Here they are. This is the square. Whoops. They're a triangle. As you can see, it doesn't actually crop because you can't actually do a diagonal crop. So you have to do crops in rectangular form. The square and then the circle here. So again, you can see there's some white space here, which we can't get rid of because cropping is unfortunately a square operation. Okay, so that's it for sorting by spatial position, well, X position here. Similarly, you can sort by top-down position by actually using the Y values here. This will give you the positions going from top to bottom, or reverse it if you want in this loop. You can set it at true here and go in opposite order. So have fun sorting your contours. So what we're going to look at now is called approximating contours. So firstly, let's open this file here. This is 4.3, lecture 4.3 here. And let's actually run this code to see what's going on. So I have a very crudely drawn house that I did by hand in Windows Paint. Thank you very much. And this is what happens when we extract contours and use the bounding rectangle for our contours. So you can see we have a bounding rectangle for the entire house, then one for the roof. So I'm guessing find contours, found contours of this triangle here. then the door, and then the bottom half of the house here. So that's pretty cool. Now the contour approx function is what we're going to look at now. And what that does, it actually, as you can see here, tries to approximate our contour shape better. So this may look a lot similar to the actual initial contour operation here. However, what it does, it actually tries to approximate a polygon to it here. So let's take a look at the function here. So you can see in our loop here, we're looping through the contours again. We found fine contours right here, and we're finding all contours and doing no approximation here. Maybe I should have done simple approximation, although it wouldn't have made much difference in this example here. So going back to our approximate poly dp function here in CV2. This is how we approximate contours. It's actually very useful if you have a noisy image with jagged contours and you know a shape is supposed to be a square or a triangle. However, you're getting maybe multiple edges in that polygon. This function actually basically approximates it for you. So let's look at the parameters it takes in here. So at a high level, I'll describe exactly what this function is doing. So it takes 3 parameters into consideration here. It takes our input contour, something called our approximation accuracy, which I'll discuss shortly, and basically whether we want a closed polygon or an open polygon. Closed being preferred in pretty much all cases, I believe. So let's take a look at approximation accuracy. Approximation accuracy is basically how detailed or how finely grained do you want the approximation to be. If you want a low accuracy, and a good rule of thumb here is 5% of the contour perimeter. However, if you go too high, I should say, with accuracy, let's look at, say, using 0.1 here. Let's see what happens. It actually does something pretty weird. It actually tries to approximate the house into the frame of the house into a triangle. That's clearly not good. So what about if we use 0.01? As you can see, it actually tries to match the house even closer. So what I suggest is that you maybe play with these values a bit. 0.3 actually works fairly well in this case here. Basically, the lower the accuracy or the ratio to perimeter, the more precise the approximation is going to be. And the higher this value here, the more larger grain that the approximation is going to be. So just keep that in mind when you're actually playing with this accuracy parameter here. Okay, so let's move on to the convex hull. And the convex hull is an interesting concept, and let's actually run the code to illustrate this. So as you can see, we have our hand here, sort of like a blurred hand right now. And continuing, we have what's called the convex hull. Now the convex hull, basically, if you can kind of figure it out from this image here, it looks at the outer edges here, and it draws lines to each edges here. Basically, it's what you call the smallest polygon that can fit around the object itself. And how it's found is pretty simple as well. So all that's happening here is that in this loop here, we're taking the contours that we found here. There's actually 2 lines of code I'll explain shortly here. It's not too critical, just something I just added in just to show you guys. And using the CV2 convex hull function, we generate a hull data type here, which is actually an array. And then we put this array into this draw contours, which takes in list function, a list variable I should say. And we just draw it over the contour itself, the image. So that's all there is to it in convex hull. It's actually quite simple to implement and use. This other line of code is actually, when you use retrieve list method, what happens is that without this line, let's just keep this, undo that. Let's just keep this here the same. So let's run the code again, and you'll see a box drawn over this image here. And what happens is that every time you find a contour on a white image here, it actually identifies the white background itself as a contour. If it was a black image, it wouldn't have happened in this way. So to get rid of that, which happens, what I tend to do sometimes is just use this little 2 lines of code here. That just, if I wanted all contours, but I wanted to eliminate that largest contour, I sort the contours by area, and I just use NumPy to index it that I want everything except the first or largest contour. And that's simply what I do here. So this is a way to get rid of that first box around the entire image. and generate just the contour that we want to look at here. Okay, so let's open up lecture 4.4, which is matching contours by shape. So let's open it here. Already have it open. So shape matching. Shape matching is actually a pretty cool technique implemented in OpenCV. So the code here looks a little bit confusing, but it's actually quite simple. So let's run the code and see what's going on firstly. So we have, this is the shape here, the template image that we're trying to find in another image. And here we go. So this is the image we're trying to find it here in. And we have identified that this shape here is the most similar to this shape here, at least according to our algorithm. And there are different methods of doing the shape approximations, or shape matching I should say. So this one here works pretty well. It actually found the closest match. So now let's see what's going on in the code here. So as I said, we load our template image in here. That's our 4-pronged star, and that's called our template image. And then we actually load our target image here, which is the file called shapes to match, or maybe you can consider it to be matched to. Alright, and then what we do next is actually first we threshold those images here. That's part of the procedure that we use in this in this code here. And then after that we find contours in the first template image. So we extract our contours in the first image. Then we sort the contours from largest to smallest, just in case there were any noisy contours or discrepancies, because we do know we only want the largest contour. And next, since we have sorted our contours in order from largest to smallest, we actually remember previously when there's a white background, the first contour is always the big box, the big white box of the image, the frame. You can consider it. So we actually have to get a second largest contour here. So we extract this contour now. And then what we do, we actually again find contours now in our target image, which was the shapes to be matched to, I should say. So we do that here. And then okay, so then we actually now loop through our contours in our target image, and this is where we actually use CV2's match shapes function. So what we do here, this is our template contour. Template contour was actually what we found previously, right here. And C is the contours in the other contour file. So remember the target file has multiple contours. There are multiple shapes in that file. So that's why we're looping through each of the contours in that file here. And these parameters here, which are different method and method parameters, these are, first method describes the contour matching type, which we'll get into in a moment. And then this parameter here, which is just basically a default parameter, don't interfere with it. There's probably going to be some work, since OpenCV is an open source project, there's probably going to be some work being done on this algorithm, but for now it's not utilized totally. So just leave it as 0. And it's actually a float 0 apparently. So what this function returns here is a match value, and basically lower means a closer match to the original image. If we were matching the exact contours, like exact same scale and size and order, the match would be basically 0. However, in this case we're looking for the closest match. So we can try different match methods here, which I'll get into in 1 second. So after we print the match value here, what we do here is that just by trial and error, I figured out that anything that's under this value of 0.15 is going to be the closest match, or the match that's closest to the star shape on the other image. So that's how we determine whether it's a match or not. And if it is a match, we make that contour that we're examining in this loop here equal to the closest contour match. Otherwise, closest contour is a null array here. And then once that's done, we actually draw the closest contour using draw contours and output it. So that's pretty much how this code works here. So let's run it one more time. See our star, and this is the contour that closest match the contour of the star. So remember I said there are actually different matching methods here, this being the third parameter in this match value, in this match shapes function. So if you go to OpenCV's documentation here, which I'll put a link in our file, actually just for safekeeping, and make this a markdown document for you guys. There we go. So if you look at this here, there are actually 3 methods here. There's contours match I1, I2, and I3, and this is the mathematics behind it, what's going on here. So feel free to experiment with it. We can just try changing it to 2 here and see what happens. It does work, and but you can see the values here are indeed different. In fact, they're pretty much all under 1.5 here. So we actually pretty much got lucky, because the last one here was actually the match, essentially. And that's why closest contour was equal to C. So you can play with this and see, try different values. That happened again here. So yeah, so that's how we match contour shape using this match shapes function in OpenCV. Alright, so we've reached the second mini project here, shape matching. So what we're going to do, we're going to take an input image that looks like this here with 5 different images, and we're going to identify each shape, put the name of the shape inside of the shape here, and as well change the color of each shape. So let's get started. Okay, so let's get started with opening the code for second mini project. That's lecture 4.5. Let's bring it up here. Okay, so I'll just tell you beforehand, even though the code looks a bit lengthy and maybe a bit confusing, it's actually quite simple. So let's run the code first and get an idea of what's going on here. So these are our input image here with our shapes, unlabeled and everything black and white. There we go, stepping through one by one. Here's a star, here's a circle, triangle, rectangle, and a square. Cool, so let's see how it's done. So firstly, what we do, we load our image in here. As you can see, when we brought up the input image here, it was just a black and white image here. So there's no real need to threshold. I just have thresholding here because it's actually become maybe a bad habit now. But the most important thing to do is actually to grayscale the image here. So loading our image here into our find contours function, we use these parameters here, train approximate none, retrieve list, which gives us all our contours, and we get extract our contours here. So stepping through our contours here, do you remember this function, approximate poly dp? Well, what we're doing here, just in case there are any edges or any other vertices that are considered when we're finding contours, which happens quite often, use approximate contours to get the approximate shape. So these are parameters that are fine-tuned for it here. However, feel free to adjust this as you see fit. So we have our approximate value here, the approximate contours here, sorry. So what we're doing now, we're checking the length of each approximate contour. If it's 3, because that's our approximated contour shape, then we obviously know a 3-sided shape, or sorry, a shape with 3 vertices is a triangle. That took a while to say. So then we actually draw now our contour. This is CNT here. We draw it over the image, and then using the moments, this is just done so we can actually place our text in the image here. And we've done this before, but you may have noticed I put -50 here. And the reason I put -50 on the x-axis here is because since it starts at the bottom right or bottom left corner, the put text here, I just wanted to pull back the text a bit more. That way, this text stays in the image. Without this, and maybe I can demonstrate it for you if you want, but without putting the -50 here, the text was sort of like skewed across the image, and it didn't look too nice. And this is the font, the color we're using, which is black, and thickness and font size. So there we go. So that's how we identify if it's a triangle here. So pretty simple so far. Hopefully you're following me well. So what about if it's a 4-sided shape? Here's where it gets a bit more complicated. Only because now that we have a 4-sided shape, it can either be a square or a rectangle. So again, doing the moments and getting the moments first just to get the labels done, right? We find actually the bounding rectangle here. Now the bounding rectangle was done so that we can determine if the 4-sided shape we have found here is a square or a rectangle. So how do we do that? So what we do, we basically just compare the width minus the height. As you remember, when you use bounding rectangle, width and height are basically the pixels it extends from the XY point. So you imagine the mouse cursor being the XY point top left here. Width is in this direction, height is in this direction. If it's a square, those values should be roughly similar. So I have here, if the absolute value of W minus H is less than or equal to 3, then it can be classified as a square. And we do it, we draw it again. This is the color we're actually filling. Remember, -1 is to fill the image. the contour. This is the color we're using here, and we're putting the text in the center again. So now let's move on to star. Now when you actually run the star through it, you realize there's actually 5 vertices in a star. And that's pretty much how we identify the star, similar to the triangle. And again, circle basically we just said anything that's more than 15 vertices will be a circle. Now this could have been set at 11, 12. I just have it set at 15, mainly because in case we actually got more points on a star, maybe because I was tuning this beforehand, maybe this should have been set to 11, but it doesn't matter right now because it's still identifying this as a circle. Because as you can imagine, even with unless we do some very non-granular approximation, a circle is going to have a lot more points than 15. So there we go. So let's run this one more time. And we have labeled all our images correctly here. So congratulations, you've completed your second mini project. Hopefully you learned a lot by using this project. So let's talk a bit about line detection. Line detection is a very important computer vision method, and you can imagine it being used in applications such as lane detection for self-driving cars, or perhaps for something that actually detects lines on a chessboard, like this example here. So the two algorithms that are available in OpenCV are Hoflines and probabilistic Hoflines. Now there are some differences between them, which I'll illustrate when we run the code, but for now I'll just talk about how Hoflines represents lines quickly. I won't go into too much detail with the math, but you may have remembered this from high school mathematics, that you can represent a straight line by this equation, y equal mx plus c, with m being the gradient or slope of the line and c being the y-intercept. However, in Hoflines, we represent lines a little bit differently. So remember OpenCV uses here as its reference point, top left corner. So what we do here in this representation, we have p, which is a perpendicular distance of a line from the origin, in this case it's pixels, and theta being the angle of this line here, normal of the line meeting this origin point here. And theta is measured in radians in OpenCV, so if you actually do open this theta value in OpenCV or access it, you'll see it's in radians. So these are some details here that I won't go into until we reach into the code, but this is basically the CV2 Hoflines function and the CV2 probabilistic Hoflines function. So let's actually use these methods now in our code. Okay, so let's open our line detection code here. That's lecture 4.6. Okay, so here we go. So firstly, let's run this code, give you an idea of what's going on. So this was a blank Sudoku board here, where we had the lines here. So as we can see, we've actually identified all the major lines here. However, we've actually left out one line here, surprisingly, and we've identified multiple lines in a few locations here. You can see there's maybe 2 lines here, 2 lines here. This one looks like 3 because there's a ticker point here. So you can see it's not perfect, and what researchers do, let me just bring it up again, they sometimes merge these lines together. They find the average of the 3 closest points and merge them together. So let's take a look and see what's going on here. So similarly in the find contours function, we've grayscaled our image, we've found the canny edges, because canny edges helps quite a bit, especially in Hofline transforms. Not transforms, sorry, just Hoflines. And these are the parameters here. So these parameters here in this Hoflines function, it takes the input image here, and then we set some accuracy parameters here. So the first parameter we set is the RAW or P value here. We typically set this at 1 pixel, but you can experiment with larger values if you wish. And then we set the theta accuracy to pi over 180 using numpy.pi or np.pi to generate our pi value here. And then this value here, this here is a key parameter. This is a threshold for determining if something is a line. So if we set this at a lower value, let's say at 150, we should get a lot more lines, way too much lines here. And if we set this at a higher value, let's say 300, we get only some few lines. So 240 was a good parameter to use for this. We missed 2 lines here, miscounted this one here. And that's the first part of the function there. So the next part of the code looks a bit confusing, but what's important to remember here is that CV2 Hofline generates this object here, lines, and lines has row and theta values inside of it. So what's going on here is that we're actually looping through all the values inside of lines here and converting it into a format where we can actually get the endpoints of lines. That's how we use cv2.line, which we went through in section 2, I believe. And we just plot all the lines that this cv2 hoflines function generates. So now let's take a look at probabilistic hoflines, which is a little bit different, and actually the code looks a lot shorter, and that's mainly because we don't need to convert it into a format, the line format, into something that cv2.line can use. It actually generates our start and end points of the lines automatically here, and also has similar parameters here where we have pixel accuracy, theta accuracy, but it also has some new thresholds here. There's a minimum line length and a maximum line gap, as well as a threshold value. And similarly, we do have to grayscale and use canny edges again. So now let's run the probabilistic hoflines function, which exists right here. And it looks a lot different. You actually see what looks like small little lines, like worms almost, on our image. And we can actually play with parameters to actually get straight lines if you want. But actually, let's bring that up one more time. What's key to note here is that because of these new parameters where we have maximum line gaps actually eliminate the need, well, the problem where we have multiple lines drawn over each other on the same line here. If we set a maximum line gap at say 5 or 10, there's not going to be any lines running over the existing line that are similar. As well as we have a minimum length of 5 for our lines. 5 pixels is quite small, but generally we can start with that if you want to get mini lines here, or lines in a character perhaps. And let's actually play with the threshold value and see what happens now. So let's set this at 50. There we go. I'm seeing slightly more lines here, but it looks generally similar. So let's actually set this at 10. Actually, it's less lines, sorry. So maybe we need to set this at a higher value. There we go. So that gives you a feel of these parameters here. Hopefully you would probably find whichever one more useful. Generally, I tend to use hoflines more, but there are definitely use cases for probabilistic hoflines. And if you'd like to learn more about probabilistic hoflines, I've actually put a link at the bottom here. This is a link to the research paper where probabilistic hoflines were first proposed. So I hope you enjoyed this lesson on line detection. Thanks. Okay, so let's talk about blob detection. So blob detection sounds a bit weird. However, if you've been in the computer vision world for some time, you would have bound to have come across it by now. So what exactly is a blob? Well, a blob, just like a real life blob, I guess, is just a group of connected pixels that share a similar property. So in this example of the sunflowers here, you can see the center of the sunflowers all have this similar green tinge here. That's basically what our blob detection has picked up. Now, the properties can be size, it can be shape, and we'll actually get to that shortly. So in general, how do we use OpenCV's simple blob detector? That's the method what we call in Python. So what we do first, we create or initialize the detector object, we input our image into the detector, we then obtain the key points, and then we draw those key points like we do here. So let's actually get into the code and do this. Okay, so let's open our simple blob detector file here. It's lecture 4.8. So here's our code for it here. It doesn't look too scary, it's pretty basic actually. So let's run this code and see what's happening here. So we've loaded our grayscale image of the sunflowers that you saw previously, and we've identified blobs in the center of the flowers here. Quite nice. So let's see how we do this. So firstly we read our image in, and previously we saw if I just putting a 0 here, we can actually call a grayscale image, load a grayscale image in here. However, this is 0 actually signifies we're writing in this line of function here. So you may have seen some OpenCV functions where we have numbers instead of the actual words here. That's just shorthand. So moving on. So the first part of this here is that we need to initialize our detector. So we call this function here, well this class actually, and we create the detector object. And using this detector object now, we run the detect method within this object here. We pass the input image into it here, and this gives us our key points. Key points being our blobs it detected. So there's no tuning of parameters here. Where there is some tuning of parameters now is basically here, where we draw the key points in the image now. However, these parameters don't affect the number of blobs that were identified. They just affect how the blobs look on the image itself. So this is pretty self-explanatory here. It's an input image. The key points we identified. So blank actually here is just one of those OpenCV type quicks. It's just a 1 by 1 matrix of zeros here, so pretty much ignore it and just use this going forward. This here is the color, which we use yellow. This is green and red here. And this is how we draw the points here. So I actually just changed this just now to rich key points, and we can see it's actually yellow now. However, initially we used the default one, which I believe was, let's undo that default there. Just looks a bit smaller, so there's no big difference there. Okay, so let's move on to our third mini project, where we actually filter different types of blobs. Because as you saw here, in simple blob detector, there's no parameter tuning here. Well, actually there is, and we'll get to it shortly. Alright, so you've reached the third mini project, counting circles and ellipses. So this is actually what our little mini project here is going to produce. We're going to count the number of ellipses and circles together here, and then count the circles separately here. And we do this by filtering blobs, which we mentioned previously. So let's get to it. Okay, let's open the code for this third mini project. That's lecture 4.9. And here we are. So let's actually run this code and see what's going on. So here we have our image here. We have some circles and some ovals or ellipses here. First, we count all the blobs or all the objects in the image. There we have 32. And now we count the circles separately, and we have 8. So let's see how we do that. Alright, let me first show you how we actually count the number of blobs and put it in the image. This one is quite simple, and you should be able to do this by now. So we firstly initialize our simple blob detector here. We pass our input image here to the detector. We get the key points, and we actually show the key points and bring it up on our image here. But what's going on here? Well, here's a very simple function. We just find the length of the key points that was generated by our detector here, and we just create a string here, and we pass the string to put text here. That's the text variable here, and that's all there is to it. That's pretty much how we count all the blobs that were detected here. But how did we distinguish between ellipses and circles? Like, how did we actually go into the key points and determine which was which? That's actually what we do over here. So here's something I haven't showed you before. We can actually pass parameters to our simple blob detector by calling this class here. This is simple blob detector underscore params. And as you can see here, there's a number of parameters here to filter on. So let me go back to the presentation and we'll discuss what these parameters are and how do we distinguish between them. Okay, so these are the parameters we're actually setting when we call simple blob detector underscore params. 4 main parameters we filter on here are area, circularity, convexity, and inertia. And we can turn each of it on or off by setting it in the code here. So just by setting params.filter by area equal true means we're actually going to filter by area. And we can set minimum areas or maximum areas and vice versa. So let's look at it here. So by setting an area, and the area is measured in pixels, to a minimum size and then giving it a maximum, if we don't set this maximum, it's not going to actually stop at any maximum. It's just going to give you the maximum of all blobs there. So setting the thresholds between here and setting is true means that we're only going to be seeing blobs that are between these two values here in area. Similarly for circularity. Circularity is a measure of being circular. It's probably the best way I can put it. 1 being a perfect circle, which means that the radius is consistent as you rotate around the circle, and 0 is being the opposite. So what about convexity? Convexity here measures basically the convexity of the object itself. So that's a pretty bad way to phrase it, but this diagram here illustrates it quite nicely. So look at the shape here, the convex shape. There's no real concave parts of the shape here. I mean, yes, there is, but it's not much. However, in this shape here, there's a definite concave thing going on right here. So if you were to draw a convex hull around this image, you'd realize that the ratio of this area here to this area here would actually be pretty similar. Whereas if you draw a convex hull around this image here, the ratio of this area to this area here is actually going to be quite high. So that's how we filter by convexity here. Now this value should actually be some value between 0 to 1, and that is basically what we consider the convexity values there. that we set, sorry. So what about inertia? Now inertia is a weird concept to think about, however it's actually very well explained in this image here. So simply put, inertia is a measure of ellipticalness, which probably isn't a word, but it probably best describes what we're measuring here. Low being more elliptical, high being more circular. So it also falls back into this circularity setting here. So we can actually set the minimum inertia to be 0.01, with 0 being basically almost like a straight line, and 1 being roughly a circle. So let's go back to the code and see how. So now, having understood those parameters, these are the settings we actually use when we're filtering on ellipses in our example file. So you can play around with these and play around with your own images as well. I encourage you to do that, because what works here for me will not always work for other images, which is why I tend to use very simple images here. This is just to illustrate a concept, not to do anything too fancy just yet. The fancy stuff is coming later on, so don't worry about it. And similarly, what happens now? Once we set the parameters here, we then create our simple blob detector after setting those parameters. So remember that. Set parameters first, then call simple blob detector here. And this actually pulls the params that were created right here. And then what we do, we actually just use the detector again to detect our key points. And having gotten those key points now, we actually do the same thing we did up here before, where we just find a length, create a string, and use put text to put it on the image. So again, that's quite simple here. And let's just run it one more time. Input image, all blobs counted, and now only our circular blobs counted. There we go. Welcome to section 5, where we talk about object detection. Now, object detection is what makes computer vision so powerful, and it's in this arena where there's so much cutting-edge research currently taking place. So in this section, we start off doing some simple object detection using template matching, which then leads us to our first mini project where we actually have to find Waldo. You can see it here quickly. Finding Waldo in this maze, or this mess of a picture here. We then describe features. Now features are very important. Features consist of corners and other attributes associated with the image. And then we look at some common and popular feature algorithms such as SIFT, SIRF, FAST, BRIEF, and ORB. And there are a couple others like Freak and Brisk as well. And we then utilize these feature detection algorithms in our second mini project, where we do some actual object detection using these features. And then we describe a bit more on histogram of gradients, which is one of the best descriptors used to describe objects in pictures. So let's get started. So why do we need to detect objects in images? Well, object detection and object recognition, they form perhaps probably the most important use case for computer vision. You can do so many powerful things like labeling scenes, such as labeling this as a digital billboard, a bus, people on a sidewalk, storefronts, or it also applies to robotic navigation in VSLAM algorithms, self-driving cars, which is actually a form of robotic navigation, body recognition through Microsoft Kinect, disease and cancer detection, things like looking at malaria slides or pictures of skin cancer, face recognition, handwriting recognition, even military use cases like detecting objects in satellite images, and the list goes on and on. There are literally so many use cases for object detection and recognition. So there is a key difference between object detection and recognition. Recognition is basically the second level of object detection. It allows the computer to actually recognize multiple objects within an image. Take example this picture of Hillary Clinton. An object recognition algorithm, probably a face recognition algorithm, would detect that firstly there's a human face in this picture, and then tries to match that face to a person in the database, this being Hillary Clinton. Now in this case here, this is one of our mini projects which we'll do in this section later on. We're just doing a simple object detection method here. So as soon as this object is held up in this little box here, it says object is found. This one only looks at one particular object and does not try to recognize exactly what it's seeing. It just waits for this image to be there, and then it tells you yes, object has been found. So let's look at our first object detection algorithm that we're going to investigate. This one is called template matching, and it's actually a very basic algorithm. What it does, it slides a picture that it's looking for in a larger picture here. So the picture we're looking for is a picture of Waldo here. can kind of see him slightly blurred. But let's bring him back down to this similar scale as this image. And what template matching does, it actually slides this picture across the image back and forth, waiting for a match. And as soon as the match is found, it actually tells you, yes, the match has been found in this point here. So let's get to it. So welcome to our fourth mini project, which is finding Waldo. Now, if you're familiar with those Waldo children's books, you basically have to find Waldo, who's this little character, in this messy maze of an image here. So we're going to now